towards francium, and that electronegativity is how much or how able an atom is able to attract an electron to itself. Okay, so we also talked about the different types of bonds and their polarity. So now we're going to look at 3 images that represent 3 types of bonds. Our options are ionic, polar covalent, and pure covalent. So remember, it has to do with how those electrons are being shared. So, and the difference between the electronegativity between the atoms. When the electronegativity is greater, the difference between the 2 atoms has a difference greater than 2. Some places you'll see it listed as 1.67. But if the difference between the electronegativity of the 2 atoms are greater than 2, that's when they form this right here, which is our ionic bond. Notice that there are 2 separate pieces. They're not sharing electrons. This one has stolen electrons away, so you've got a positive charge and you've got that negative charge. Polar covalent is when the electronegativity difference is less than 2. So they have different electronegativities, but not more than a difference of 2. And in that case, they are going to share electrons, but one is going to steal more electrons than the other. That is where you can see this happening. It's more likely for an electron to be on this end, on the negative end, than it is on the positive end. So this is our polar covalent. And then finally, you have that electronegativity difference of 0, which is the pure covalent, where everything is equally shared. You guys at different points will be given a periodic table that has electronegativities on them. So I have a green copy of one right here. So this is a periodic table that has these numbers are their electronegativities. So when we say the difference, we're literally looking at when we subtract the 2 numbers, what is the difference? So if I was, lithium and fluorine, if I said that those 2 things were going to bond to form lithium fluoride, then 4 minus 1 is 3, meaning I know it's an ionic compound because it has an electronegativity greater than 2. But on the other side, if, oxygen and nitrogen were to bond together, okay, NO2, I know that that is a covalent bond, and it is going to be slightly polar covalent because it is greater than 0, 3.5 minus 3, but it is less than 2. So it would be slightly polar, 0.5 difference. So the bigger the difference, the more polar something's going to be, and then the closer to an ionic compound it'll be. So we can use the electronegativity to determine those bond polarities. So here's a chart. This is copied very strangely. I don't know why it copied so poorly. So we're going to write these out so you guys can actually see them. But we're going to use the electronegativity values given to us to arrange the following bonds in order of increasing polarity. So the larger the difference when we subtract, the more polar something is. So what we have here is we have a hydrogen and a hydrogen. We have a sulfur and a hydrogen, chlorine and hydrogen, oxygen and hydrogen, and fluorine and hydrogen. So these are all different elements that are going to be bonded to hydrogen. We give us the electronegativity values. So they tell us that hydrogen's 2.1, sulfur's 2.5, chlorine is 3.0, oxygen's 3.5, fluorine is 4.0. We would have to give you those values, or we would give you something like this chart and have you guys look them up. So those are the first atoms pieces to figure out the electronegativity. Then you subtract whatever the second piece is. These all happen to be hydrogen. So hydrogen we know has an electronegativity of 2.1. So from all of these, I'm going to be subtracting 2.1. So when you subtract, this one comes out to be 0. This one comes out to be 0.4, 0.9, 1.4, and 1.9. So this one we would label, you can tell here, is covalent, which is pure covalent. And then the rest of these are all polar covalent. They're all polar covalent compounds, with the polarity increasing as you go down, because these numbers, the difference between electronegativity, get larger and larger. This one, in some texts, could even be considered ionic, depending on who you talk to, because that 1.9 is so high. So all of these, as you go down, the polarity gets larger and larger, it increases. So as you go across this list, the polarity goes from least polar to more polar. All right, so in our last set of notes, I mentioned the word dipole. So, and I said dipole moment. What that is a dipole moment results when a polar molecule has a center for positive charge separate from a center of negative charge. So you get this sort of positive and negative situation happening. We always draw it with a positive side and an arrow going to the negative side, showing the fact that these things are being pulled with a slightly positive or negative charge. Water is something that is very common to be talked about as having a dipole moment. So it has a positive center and a negative center. Those hydrogens each have a slightly positive charge, whereas the oxygen has a slightly negative charge. And so what you get is this overall situation where the left-hand side is positive and the right-hand side is negative. Water being a polar molecule and having this dipole moment is why it's able to dissolve ionic compounds within its solution, make aqueous compounds, because you get these positive and negative ends pulling on these pieces and they pull it apart. Here you can see if this is a positive ion that's supposed to be showed here, this is a negative ion. So you can see here the negative ends of the water molecules pulled on the positive piece, whereas the positive ends of the water molecule pull on the negative piece. And so therefore you get this splitting effect that happens where those things are pulled apart in solution. And when the water goes away, that's why they bond back together. This is also what allows water to remain liquid at a higher temperature. Okay, so that is the finish up on 2.1. The rest of today's notes go into section 2.2, which is dealing with our picture with a Sneezy. So here the objectives are to learn about stable electron configurations, learn to predict the formulas of ionic compounds, which we already basically know how to do, or you should know how to do, to learn about the structures of ionic compounds, understand the factors that govern their size, and this is a little bit of review. So you should know at this point, when you look at the periodic table, the general trends on how ions are formed. You should know that group 1 always form positive 1 charge, group 2 always forms positive 3. Things like aluminum in group 3, positive 1, positive 2. I think I said positive 3. So positive 1, positive 2. This grouping here, for the most part, towards the top, you get that positive 3 charge. Then in the fluorine group, you get that negative 1 charge, and we get negative 2 charge here. Okay, as we get into these higher ones, negative 3 or positive 4, some of these form those. Other pieces are not as secure, but it has those trends that go through there. So one thing we should point out and talk about and refresh our minds with is that all atoms always want to be like the noble gases. Noble gases are those gases on the very right-hand side of the periodic table that are not, they're called those inert gases. They don't bond with other things, and they have 8 valence electrons. That is the best situation to have. They have a completely full valence shell, which makes them more stable, makes them less likely to bond with other things, and just makes them overall happy. The way to remember that is you can say, after I ate, I am full. So you have 8 electrons and you're full, and therefore you're more happy. So the reason things form their ionic charges that they do is because they are trying to have electron configurations like that of a noble gas. So if you look, anything that's in these charges, once they're in their ionic state, their ionic electron configuration will always match that of a noble gas. So I think on the next page, I think the next page really shows it to you better, although that image is kind of hard to see. Let me pull up, I have a digital version of this. Let me pull it up real quick. All right. Just bear with me 1 second. No, not that one. I'm just pulling up the digital copy of your notes so you guys can see a little clearer what it's doing. Okay. So here we can see just a little bit better what exactly is happening. So here you have sodium. Sodium, if I was drawing out the electron configuration, if I was using the noble gas notation, sodium is 3s1 is where it stops. So if I wrote the noble gas notation, it would be neon plus 3s1. But